Hooke's law. Okay, so Hooke's law is the force required to maintain a spring stretched X units beyond its natural length is proportional to X. Okay? So this works, Hooke's law works as long as X is not too big. All right? So what does this look like? Hooke's law, f of x is equal to kx, where k is known as the spring constant. Now, k is a positive real number, okay? So k is positive and it's a real number. It's an element of the real numbers, all right? It's positive. So Hooke's law states that the force required to compress or stretch a spring X units from its natural length is proportional to X, okay? So for example, if a force of 1 Newton stretches a given spring 2 centimeters, then the force of 5 Newtons will stretch the spring 10 centimeters. Converting the distance to meters, we have that stretching the spring 0.02 meters requires a force of F times 0.02 equal to K times 0.02, which is equal to 1 Newton meter. Therefore, K is 1 over 0.01, which is equal to 50 Newton meters. So let's run through an example. All right, let's run through an example here so you can see what I'm talking about. Force of 40 newtons is required to hold a spring that has been stretched from its natural length of 10 centimeters to a length of 15 centimeters. Okay. How much work is done in stretching the spring from 15 centimeters to 18 centimeters. Okay? So, to do this, I need a force function. The force is equal to K times X. Now, what I need to do is figure out what K is. To do this, I see that a force of 40 newtons is required to move the unit from 10 to 15. Now, I don't care so much about 10 to 15. as much as I do stretching from its natural length to this new stretch. So its resting length, the spring, is 10 centimeters. Okay? But I stretch it out, and I stretch it out, and it becomes 15 centimeters. But to do that, it took 40 newtons of work to do that. Okay, 40 newtons of force to do that. Sorry. So the amount of distance traveled here from 10 to 15 centimeters is 5 centimeters. Now 5 centimeters, remember with force, we need it to be in terms of meters, right? Okay, so 5 centimeters is 0.05 meters, right? So the distance x that it's traveled is 0.05 meters. I don't know what K, the spring constant, is, but I know that a force of 40 Newton meters was required. So if I divide both sides by 0.05, so 40 divided by 0.05 gets me 800 for K. Okay? So this tells me that my force function is equal to 800x. All right? That's going to be helpful because in order to figure out how much work is done, that's the integral from work is A to B force function integrated. So once I have my force function, I just got to figure out what A and B are. Well, how much work is done by stretching it from 15 to 18? Well, let's think about this. Remember, the resting length was 10 centimeters, right? And then, so what I want to know is what work was done to stretch from 15 to 18. So instead of stopping at 15, now I stretch it out to 18. Okay, so 18 centimeters. All right, so that work goes from here to here, right? So how far is that stretched beyond? Well, starting at this value here, that's stretched 0.05 meters. But from here to this value there, so this second part up here, that's stretched to 0.08 meters. So I need to figure out how much work is done in this orange area here. So that's equal to the integral from 0.05 to 0.08 of the force function, which is 800x dx. And if you integrate this, you get x squared over 2, 800, that's 400, evaluated from 0.05 to 08. And this ends up getting you 1.56. And work is in joules. Okay, Newton meters. All right. So units are important here. Make sure you're paying attention to your different units.